Hello, hello everyone. Hello. Good morning, everyone. Uh, shall we start? Okay. Um, for the last lecture, we have already seen that what do you mean by the operational amplifier and what are the different kinds of configurations of the op-amp can use. So we have already seen that there are the four kinds of operational amplifiers configuration. Which are that? These are nothing but dual input, balanced output, dual input, unbalanced output, single input, balanced output, and single input, unbalanced output. Okay. So again, I revise that what how we are going to distinguish all these four different configuration is that dual or input, dual or the single. It is just going to be configured that how many inputs are given to a transistorized differential amplifier circuit. So if we are using only one input circuit, that is one input to the base of the, that we have already seen, that is this kind of an inputs. So if I am using only one input source by keeping the other as an a ground, then it is called as an a single input. If I am giving the both inputs both to the I give the input voltage to both of the base of the transistors, that is V1 and V2, then it is called as a dual input. And what about the balanced or unbalanced input? That if we are taking the output with respect to ground, here it is an a VC, so here is nothing but an a collector voltage. If we are measuring it with respect to ground, then it is nothing but called as an unbalanced output. And if we are measuring the voltage across the collector terminals of the two transistors, then it is nothing but called as an balanced output. So we have just seen about these all kind of configurations. We have already seen in detail about the dual input dual input balanced output differential analysis. Okay, so in that we have just seen that how it is going to be work and all that kind of parameters. Now today we are going to see the in detail, we are going to see the dual input balanced output differential analysis. We are going to study it with the help of two kinds of an analysis. That one is nothing but an DC analysis and AC analysis. Okay. As we have already seen that operational amplifiers are able to access the both of the parameter, that is an AC parameters as well as an DC parameters. So we are going to relate with their analysis in the form of we are just going to be concentrate over here as one configuration, that is dual input balanced output differential amplifier. So firstly, let's start. So firstly, we are going to concentrate on the first parameter. It is nothing but called as an DC analysis. We have no, just to remind the amplifier, that one is nothing but an dual input balanced output kind of it is nothing but an dual input balanced output differential amplifier. Okay, we have already noticed that the two input signals, that is called as a dual input. It is nothing but an V1 and V2. In some books, it will may be referred as a V in 1 and V in 2. These are applied at the basis of the V1 and V2 of the transistor Q1 and Q2 respectively. we are measuring the output voltage V0 in between the two collectors, that is on a C1 and C2, which are at an same DC potential. We have just assuming that which are at an same DC potential. Because of the equal DC potential at the two collectors with respect to ground, the output is referred to as the balanced output, isn't it? As both of these VC1 and VC2, they having the same DC potential with respect to ground, then we are measuring the difference between them, and that's why it is nothing but called as a balanced output. Okay, now for the today's session, what is my aim is that we are going to deal with an DC analysis of the dual input balanced output differential amplifier. So first of all, what is we are expecting with the help of an DC analysis? So in the DC analysis, we are concentrating on on we are able to obtain the operating point parameters of the values, that is nothing but the ICQ and VCEQ values. Okay, in detail you can see, you can study about this one in your ESD subject, but in short, whatever is required, I am going to be explain this. So ICEQ, Q over here, it is an operating point. This operating point is useful for analyzing the transistor's work. That is, transistor can be work in a different kinds of modes: active mode, saturation mode, and the cutoff mode. It is best on which region, it is best on the Q point operating regions in this place. So if it is to work the transistor as an amplifier, we should have to be kept it into the active region. Okay, so we are obtaining that with the help of the operating point is going to be determined. It is going to be analyzed with the help of two values. One is related with voltage, another one is related with current. So we are considering voltage at VCEQ. It is EC means voltage between collector to emitter related with Q point. ICEQ means the collector current with respect to Q point. So our basic aim to analyze these two kinds of values. Now we need to obtain for the to just go for the DC analysis, we need to obtain the DC equivalent circuit. Okay, this DC equivalent circuit can be obtained by simply reducing the input voltages V1 and V2 to 0. Okay, so how we have just measured down, this one is with the this one is nothing but a dual input balanced output differential amplifier, which we are using for the DC analysis. So we are keeping this kind of an input source voltage towards the towards as an 0. Then DC equivalent circuit will be just appear as over here. Now, the internal resistance of the input signals are denoted over here as RS1 and RS2. But as we have already seen that we are assuming these Q1 and Q2 are identical in all respects, so we can say that RS1 is nothing but equal to the RS2. Since both of the emitter bias junction of the differential amplifiers are symmetrical, this one is differential amplifier. This both of the emitter bias sections, both we have already seen that Q1 and Q2 are identical in all respect. That is, RC1 is equal to RC2, RE1 is equal to RE2, IB1, IB2 both are equal, and hence we can say that both are identical in all respect. So we can measure the so we need to determine the operating point, that is on a collector current ICQ and collector to emitter voltage VCEQ only for one section. That one is sufficient. So let's start. We are going to just concentrate to calculate the value of firstly the collector current value. So we are using some kind of an KVL, that Kirchhoff's voltage law. for the base emitter loop. This is nothing but this one is the base of the transistor, this one is a collector of the transistor, this one is an emitter of the transistor. I have already explained the configuration of this, that is a dual input balanced output differential amplifier. This RE, it is nothing but the RE1 parallel to the RE2. Here the current in this branch will becomes as an 2IB. Why it is? Because this IE1 and this IE2 both are in series, and hence the net current flowing through this emitter resistor will becomes as IE1 plus IE2 is equal to 2I. Okay, now we are applying the KVL for this base emitter junction. Okay, so you have already studied that about this KVL, Kirchhoff's voltage law equation, how it is going to be applied. Okay, so how it will becomes as the first one, we are moving from ground towards the supply. So it will becomes as first one, first voltage drop will be takes place across this resistor. The current flowing through the resistor is an IB. So it will becomes as minus. We are moving from ground to the supply. Okay. So it will becomes as RS. Yes, you have. I'm just kindly requesting you that you put down this kind of put down this figure, and also calculate the apply the KVL at the base emitter junction, and then you parallelly just go with me, just take out your pen and paper with you and just draw this figure and try to apply the KVL. I am also going to be explaining, just be with me. Hello. Okay, shall we start? Okay. So what we require, that is first of all we should have to apply the KVL. So it will become as, minus, as we are moving from this to this direction, your supply is this one. Okay, so it will become as minus RS1 IB1. Yes, this is the first voltage drop. Then the voltage drop across to base to emitter, it will be again comes as a minus of, will becomes as, it will be moved from this direction to this, that is we are moving from ground to the supply. So it will becomes comes towards, that is in the opposite direction, so it is coming as a minus of VBE. This is the voltage drop. Then what is the next junction? It will be comes towards the RE. So here it is an RE resistance, current through that it is nothing but an 2IE. So it will be again comes as a minus 2IE RE. Then minus of this minus VEE is equal to 0. Okay, minus of minus this VEE is equal to 0. That means what we have just carried out over here, I will be again going to show you, that is how we are just going to be calculate what is the we have just carried out over here. It is, yes, it is nothing but minus of RS, minus of RS IB minus of VBE, then minus of our minus of RE into minus of RE into 2 minus of RE into 2IE. Yes, minus of RE into 2IE minus of, then minus of VE minus of VEE is equal to 0. Okay, so if we will be try to solve this, it will becomes as this minus of minus v will becomes as a plus v. Okay, so we are just coming over here, it is nothing but minus of, it is nothing but minus of rs into ib minus of it will becomes as a minus vbe. All of you please try to solve it with myself. Okay, minus of this minus of re into minus of this re into bracket, it is of an 2 e, yes, and this minus minus, this will becomes as an plus 1. Okay, this will becomes as an plus 1 plus of VEE. Now when I will be just move this one towards the another opposite side of this equation, that is equal to, this one is equal to 0, and when I will be move this one minus VEE towards this one, it will becomes as a minus V. Then if I change all the signs, then it will become as, that is when it will be moved towards this side, it will become as minus of rs into of ib, yes, minus of this will becomes again as an vbe, yes, and then it will becomes as minus of 2ie into minus of 2ie into re. Now this plus VCC VEE will become on this side, and it will become as is equal to minus of VEE. So if I will be change the all the signs of this equation, minus of minus VEE, then it will becomes towards the which kind of a parameter, it will becomes like this one. Okay, isn't it? So it will becomes as rs into ib plus of vbe plus 2iere is equal to ve. All of you get it? Now this nextly we are going to replace, we will be required as an IC value, remember. So this one is a collector current. Remember, if the transistor is ideal, we are assuming that whatever the current is entering into the collector terminal, it may be same available as an emitter current, due to no any drop will be takes place across this journey. So in short, we are assuming that IC is nearly equal to of IE. So either of one value we are able to calculate, then we will be get the collector value. Okay, and that's why it is important that we have to nullify all the parameters related with a base. So this base current is going to be replaced in a form of an IE. This one is nothing but called as another. IB value is given as IB is equal to IE divided by beta DC. What is this beta DC? Beta DC is nothing but of an current gain. You will be just see this one in detail in the your EST subject. So this one is the collector gain. It is given with IE divided by IE. IE is nothing but an output current divided by input current as an base. Gain is nothing but output divided by input quantities. So this one is on a current gain. Current gain, it is in a form of a collector current gain, which is given by IE divided by IB. And with that basic equation, we can calculate that IB is equal to IE divided by beta DC. And as I have told you that IC is nearly equal to the IE. So we are just putting down this value beta DC over here and just going to be replace this RS divided by beta DC. Okay, again we are dealing with the same equations over here. So what is the parameters that we have just carried out over here, that we are going to be just you are just over here this one kind of an equation with the you are just at this equation. So it will becomes as rs into bracket IB is going to be replaced with, now it will be replaced with the IE divided by this kind of an beta DC value. Okay, so beta DC minus of this VBE minus of this VBE minus of 2, it will becomes as IE into minus of 2IE into RE, isn't it? Minus into 2IE RE is equal to VEE. It will becomes like this one. Now we are going to be rearrange this term, that is we are just going to see it is RS divided by of beta DC, so that I can just collect all the emitter values together. That is we are just going to be rearrange this beta DC with this part, that is RS divided by beta DC into of this IE minus of these 2. I just going to be just carried out this one, sorry, it will becomes as a plus. All the values are going to be changed. Okay, so this one is a plus, so it will becomes as a plus, it will becomes as a plus 2 IE into RE, IE into RE plus of this VBE. Okay, so plus of this VBE is equal to VEE. Okay, this will becomes as it is with the same values. Okay, now the nextly we are again going to rearrange all these. We are taking the all common points about this IE. This one is IE, this will also contains IE, so I can be write over here, that is IE into bracket, IE into bracket, it will becomes as RS, it will becomes as RS divided by of my beta DC plus of 2RE plus of 2RE into bracket into of 2 VBE into of an 2 VBE is equal to, it will becomes as 2, it will becomes as an VEE over here. Okay, now what is our aim? Our aim is to calculate the IE. So to calculate IE, I should have to be first of all subtract this from the VE and then go for the rearranging the same one. Okay, so the same one we will be just carried out over here. That is by answering it will becomes as VEE minus of VBE divided by 2 RE plus RS of beta DC. Okay, so this in this way this equation will be arrived. Okay, all of you get it? Is there any doubt? Please drop your message in the chat box. Are you get it? Just realize if you have any kind of a doubt, please ask me. So in this way this equation is going to be carried out. This equation will be appears over here. Okay, now nextly we have to we are able to carry out able to obtain the value of the emitter current, which is we have assumed that similar as an IC. Now this VEE is nothing but a negative emitter voltage, and VBE, this one is nothing but a base to emitter voltage. This base to emitter voltage is on a constant value. It is nothing but 0.6 volt for the germanium and 0.02 for the whatever the transistor material, silicon and germanium. These are the two materials used for the construction of the transistor. Depending on that, that is 0.6 it is for the silicon, and this value is 0.2 for the germanium kinds of a transistor. Okay, so this value is constant. Now this beta DC value, beta DC is a quite larger value as compared to the RS, and when this large value is going to be divided, obviously this value will be comes as a very less as compared to the 2RE. Okay, so this one is a value, it is going to be divided with a larger value, so this division value will becomes as a very small one. So we assume that we can say that this value is very less as compared to the 2RE, and that's why it is going to be ignored, and hence finally this equation is going to be reduced as IE is equal to IC is equal to VEE minus of VBE divided by 2RE. So in this way we are very much successful to derive the equation about the collector current. Now from this equation we can say that what is the final value? You can get the collector value with three parameters, one of VEE, another one is VBE, and second one is called as RE. Okay, So out of that VEE, it is as the negative supply voltage. That value is constant. VBE, it is the again constant value, and then only variable value will be remains as the resistor, emitter resistor. Okay, so we can say that whatever the value we will be required for the collector current, it is wholly dependent on the emitter resistance. It is the value. Okay, all of you get it? So please be remember that collector current is equal to, it is nothing but of your this voltage divided by current is nothing but an voltage divided by resistance. Okay, so voltage, what is the voltage total drop? It is nothing but an VEE minus of this VBE divided by this 2RE. Okay, so this one is in this collector voltage. He is just crossing with the first voltage drop across B. Second voltage drop is going to be considered about VE. So you can remember in this way, that is VEE minus of this VBE divided by 2RE. So we will be come to the, with this equation we will be come to some kind of a conclusions over here. Whatever we have discussed, that is I have just summarized in this slide. That is the value of RE set up the emitter current in a transistor Q1 and Q2 for the given value of VEE. Given value of VEE. The emitter current in the Q1 and Q2 are independent of the collector resistance. In this equation, there is no any value about the RC. Though we are calculating the IC, the no any value of the RC will becomes over here. So we can say that it is independent of the collector resistance. The voltage at the emitter of the Q1 is approximately equal to the minus of VBE if the voltage drop across the RS1 is negligible. That we are assuming. Knowing the value of the IC voltage at the collector, VC is given by. Now we are just going to carry out the second one, that is second parameter that we required for the Q point analysis is nothing but the collector to emitter voltage. Okay, so this one is, are you any doubt for the calculating about this collector voltage? If you get this, the same concept we are, or the same step we are going to be apply for the calculation of the voltage. Okay, so please remember IC is nothing but the voltage drop. Current is given by voltage. We use this kind of common sense, that is current is given by voltage divided by resistance. So we are taking the voltage drop as VEE minus of this VBE divided by this 2RE. So the IC value is totally based only on the value of the emitter resistance. Okay, now just analyze this equation, please. I will be give you the 2 minutes for you. Just analyze this equation. If there is any doubt, please ask me. Otherwise, you will be not get this kind of concepts over here. Okay. Now, please be fast. Okay. Now, next up. We are going to calculate the collector. What is the next Q point value will be required? We required the VCEQ. VCE, V voltage, C for the collector, E for the emitter. So we are calculating the voltage drop across from collector to emitter. It is nothing but called as the VCE, collector to emitter voltage. So again we are the voltage at the emitter of the transistor Q1, the voltage at the emitter of the transistor Q1 is nearly equal to, what is this value? Here it will becomes as, we have already seen, it is nothing but a minus of VBE. If we assuming the voltage drop across this R1 is to be very, very small. Now, knowing the values of the emitter current, its value is equal to the collector current. Okay, we can apply the KVL, and we are trying to get the voltage at the collector of the transistor, which one is called as firstly we are carried out this VCE. Now, what is our basic aim is that we required a voltage drop of we required the voltage, which one? VCE. V, that is a voltage drop across the collector to emitter. This VCE value will be nothing but the subtraction of the voltage at the collector and subtraction of the voltage at the emitter. So our first step is that we are calculating this collector voltage. Then next step is we are trying to calculate the emitter voltage, and then we are going to be subtracting. Okay, this is the step. Now firstly, we are trying to calculate the collector voltage VC. So how it will becomes that collector voltage, this one is on a VC. So we are moving in this branch. So here there is, this one is on a VC. So it will becomes as on a VC is equal to nothing but the VCC minus of this ICRC. Am I correct one? Am I correct one? So this one is VCC minus of I1 R1 is nothing but of an VC. Okay, so I have just drawn over here, that is simply a collector voltage we have written over here. Now as I have told you that VC is nothing but collector voltage minus of emitter voltage. Now to get the emitter voltage, we are trying to apply the KVL again for this one. We are trying to apply the collector to emitter voltage. How we will be comes to the collector to emitter voltage? What is this? Yes, collector to emitter voltage. What, how we come to the that this VC, put down this VC value as it is nothing but an VCC minus of this ICRE. And what is this VE? VE is nothing but your emitter voltage. We have already seen that. What is this emitter voltage is equal to? What is this emitter voltage? It is mostly nearly equal to the voltage drop from base to the emitter. Okay, because we have just considered that this transistor Q1 and Q2 are identical, and this RS voltage drop across this RS resistor is very negligible. That means here it is not as good as not present. So whatever the drop will be takes place across the base to the emitter, the same value is available at the emitter terminal, and that's why we can say that the emitter voltage is same as that of the voltage drop from base to the emitter. And that's why we are writing that minus of V will becomes as a minus of E as we are moving from ground to the supply. And that's why it is minus of minus VBE will becomes as a plus 1. So in this way, we will be just saying that this VCE is equal to VCC minus of ICRC plus of VB. Now what we are required, that is this one. So we are just going to be coming to the conclusion that the collector to emitter voltage is nothing but the addition of the two voltage minus voltage drop, this one across the collector terminal. So it will become as VC is equal to VCC plus of VBE minus of ICRC. Okay, please note it down. This one is very important. So this in this way, with the help of an DC analysis, we are very much successful to calculate the collector value and voltage across collector to emitter. So these are the two values you should have to be remember. Please make a box over here and remember this one. This is important for solving some kind of problems. That is, IC is equal to voltage divided by resistor. So it is nothing but VEE minus of VBE divided by 2RE, and the collector to emitter voltage VCQ is equal to VCC plus VBE minus of ICRC. Okay, so all of you guys, please, it is a kind request to all of you, just again go through these two kind of an equation. If you have any kind of any doubt, please you ask me individually. I will again explain you. Otherwise, if you are very much easily get understand this, then we for the next lecture we are moving towards our next point, that is nothing but related with AC analysis. Okay, all of you get it? Is there any doubt for this one? Just only one minute is remaining, so be fast. Put down your any kind of messages on the chat box so that I can be connect with you. Okay, so again I am requesting you, just again go through this kind of equations, this all kind of analysis, and if you have any kind of doubt, please ask. Okay. Okay, okay, thank you. So this one is okay for today's session. Thank you very much.